Okay. So 17.2 is about reaction rates, which we also call kinetics. Kinetics is the study of the rate of a reaction, which is basically how fast the reaction happens. And one way that we can calculate the rate of a reaction is we can graph concentration versus time. And if we graph concentration versus time, we'll see that the reactants are going to go down and the products are going to go up proportionally. And basically, this is the slope of that line. Okay, I did not pull up Jamboard. Let me get that pulled up here. I'll use Keep. And make a new one. Okay, so if I were to graph, like I said, concentration over here, and concentration is sometimes abbreviated as a bracket, and it's usually in molarity, which is moles per liter, versus time. I'll have my reactants. Let's say this is A turns into B. Okay, so this reaction, A is turning into B. A is going to start with a high concentration because at the beginning of the reaction, you only have A, and it's going to go down. Okay, and there's a few options. Usually it kind of like levels off right somewhere below where it started. And B is going to go up like so. And then if A levels off, B is going to level off and look something like that. So this is the concentration of A going down, and this is going to be the concentration of B going up. And how fast is the reaction happening? Well, that is going to be our change. Remember this little delta guy means change. And I can look at, if I want to measure how fast a reaction is going, I can look at how fast are the reactants going away, like disappearing, or I can look at how fast are the products being formed. So change in A over change in time. Okay, and because A is going down over time, if I looked at the change, it would be final minus initial. That would give me a negative number. And for rates, we always want a positive number. So that's why there you'll see a negative out in front. That's going to be, I'm just going to put a little R for rate. That's going to be the rate of our reaction. How fast does this change over a given time? And you'll notice that the slope of the line, this is not a constant slope where it would just go down and hit at zero concentration. But it starts off kind of steep. So there's a high slope right here, and then it kind of becomes less steep, and then there is no slope right here. So the change in concentration would be zero over the change in time. So this, there's nothing going on here. Okay, there's no change in those concentrations. So the reaction has, we're going to learn later, come to equilibrium about right here. About right here where they stop changing is where we're at equilibrium now. So this chapter is about the left side of this chart, and the next chapter is going to be about the right side. Okay, and if I looked at the change in concentration of B, delta B over delta T, we should get the exact opposite. So as fast as this one's going down, this one is going up, because you're taking A and you're turning it into B. Okay, so that's the way that we find the rate. And we don't need that negative because this is increasing, so it's going to have a positive slope. And really, if we look at like a math perspective, this is a graph, And this is just the rise over the run, which is the slope of the line. So the slope of the line is the rate at that point. Okay, and if you get really fancy and go on to calculus, you'll learn what's the derivative. So I can pick just a single point on here and I can find what is the slope at that exact second. And then that's the instantaneous rate, but that's way ahead of where you guys are at. It's college level stuff, okay? So all you need to know is the rate of the reaction is how much the concentration changes over a specific time. For iron rusting, you can look at the iron going away, but more likely we're going to measure how much rust is forming on there. So we'd be down here, we're going to look at how much rust forms over a given time. And for that reaction, you have a really long time because it takes years for iron to rust. So if you had like 2 years down here in seconds, you're going to have a really big number down here. And that means that this rate is going to be really, really small because you're dividing by a huge number down here. Okay, and the change, how much rust there is actually tiny too. So both of those things lead to a really small rate of the reaction. Okay, let me go back to the notes. All right, so that is how we calculate rate. What determines the rate? Rate influencing factors is what causes the rate to be fast or slow. For iron, it's just a matter of the electron configuration of iron. Iron happens to be pretty stable, so it's happy with its electron configuration. It's low energy, and it's not likely to change. So that's why it happens really slowly. For sodium, remember I put sodium metal in water, and it dances around, and then every once in a while it bursts into flames and sometimes explodes. That's a very fast reaction, and then it's over. So some elements like sodium are just naturally more reactive than others, and that's because of their electron configuration. Because sodium just has that one valence electron, it's very reactive. Okay, so we can't do anything to change the nature of the element that we're using. We can change these three things. So surface area is how much of the surface is exposed in a reaction. A heterogeneous reaction is a reaction in which they have different phases. So the sodium in the water, you'd have a solid and liquid, and that would be a heterogeneous reaction. More surface area means the reaction happens faster. Okay? And we see this all the time, so we're very familiar with this. For example, if you want to start a fire, you wouldn't take a giant log and put it in and try to light it. You have small pieces that you light that can then help like a chain reaction, light the bigger pieces of wood. So you want smaller pieces, which is actually more surface area, because if we just had one big, or let's look at sodium, because that's another really good example. We just have one big chunk of sodium. The only part that the water can reach is on the surface of this big piece right here. Okay, so if I want this to react very quickly, this is going to react pretty fast, but if I cut it in half down here, then now I've exposed everything on the inside of these two pieces. So I've increased the surface, and if I cut it in half again this way, now I've exposed the inside here and then the inside along here. So there's a lot more area that the water can reach of the sodium, causing the reaction to go even faster. So if I timed the big chunk versus these four small, these rectangular prisms, the four smaller pieces will go a lot faster. Okay, so that's surface area. And if we were working with some kind of like ionic thing and we want it to react really fast, we could grind it down into like a powder, because that would have a huge amount of surface that would be exposed. So it should be almost explosive at that point if we grind it up to teeny tiny little powder pieces. And that's why coal dust is so dangerous, actually, because the dust can react with just the tiniest little amount of energy. The dust explodes. So coal dust is not a good thing to have in like a coal mine because it can explode. All right, temperature. What would this blank be, can you guys put it in the comments? Higher temperature means the molecules are moving. Anybody? I'm waiting for the comment in the chat. Higher temperature means they're moving what? Faster. Good job, Eileen. Okay, hi guys. We're going over 17.2 notes. So this blank right here was faster. If they move faster, they're going to collide more often, and also they have more energy when they collide. So this is a 2-for-1. When you have a higher temperature, the reaction speeds up a lot because you have more collisions, and those collisions have greater energy, so they can get over that little hill that we talked about last time, which is the activation energy. Okay, and then lastly, concentration. If you put more molecules in the container, then you're going to get more collisions. So this whole thing boils down to, if you have more collisions because you have a greater surface area or a higher temperature or greater concentration, more collisions equals a faster rate. Okay, so this is the most important part of all of that. More collisions equals a faster rate. So if you can do anything to increase the number of collisions, then you can increase the rate of the reaction. And there's a really funny video on how to speed up a reaction and get a date, and you guys should watch that because it's funny. Okay, and very accurate. The goal of the standard for this chapter is for you guys to manipulate a reaction to make it react faster, basically. So you're going to want to look at these 3 things and see how you can change them to make the reaction speed up. All right, presence of a catalyst. A catalyst is just something that helps a reaction go faster, but it isn't used up in the reaction. And in our bodies, we have a ton of these catalysts. They're called enzymes. So like the reaction of digestion, it's sped up by a lot of different enzymes in our body. If we didn't have them, then the digestion of food would take so long that we couldn't get energy to our cells fast enough and we would die. So we need those enzymes there to help us break down the food and do a million other things that our body does every day. Okay, so that's a catalyst. It lowers the activation energy. Sometimes they can even help grab onto the reactant molecules and align them into the correct orientation so they're lined up properly, so then they can react better too. Okay, and this is just a little picture of what a reaction would look like without a catalyst. The blue line is the size of the hill that they need to get over. So you have your reactants right here. They are higher in energy than the products, so they do want to be over here. This is more stable. But they have to get over this big barrier of the activation energy to do that. So only molecules that collide with this much energy can get to the product side. When we add a catalyst, we're lowering the size of the hill that they have to get over to react. So this red line is with a catalyst. So you can see it'd be a lot easier to take a boulder and push it over this little red hill to get down here than it would be to push it over this one. So it lowers activation energy, and that means more of the reactants have enough energy to get over the hill so that they react faster and they turn into products faster. Okay. A homogeneous catalyst is a catalyst that is in the same phase. So a catalyst for a gas reaction in the atmosphere, for example, the ozone layer, that is a good thing in the stratosphere. It protects our skin from the ultraviolet radiation. Chlorine from chlorofluorocarbons speeds up the decomposition of ozone. So those are all gases that are floating around in the atmosphere, and that would be a homogeneous catalyst. It speeds up that reaction and the ozone goes away, and that's why those were a bad thing, and then they were banned, and we're trying to fix the problem of when we put all those CFCs into the atmosphere in like the 80s. Okay, a heterogeneous catalyst is in a different phase. So another example is when we run our cars, we have a catalytic converter in the back of the car usually, and it's solid, and it's usually metals like platinum, and the gases from the exhaust go through that catalytic converter, and they turn harmful gases like carbon monoxide into not so harmful gases like carbon dioxide. Okay, so that's what a catalytic converter does, and that's a heterogeneous because it's solid and the reactants are gases. Okay, enzyme, we already said that. The rate of the reaction depends on the frequency of collisions. So how often are they colliding? More collisions means faster rate. And the efficiency means that they have enough energy to get over this hill. And also they have to bump into each other with the right orientation to be efficient. Okay, that means it's actually gonna, when they do collide, it's actually gonna react. So they have to have enough energy and the right orientation. Okay. Which frequency or efficiency do enzymes facilitate? That's kind of a trick question. Do you guys want to answer in the comments, in the chat? Frequency or efficiency? Which one of those do enzymes help with? Anybody know? Enzymes help to speed up the reaction. Is it the frequency of the collisions that they help or the efficiency of the collisions? Okay. Yay, Ariana got it. So an enzyme is going to make sure they're aligned properly, remember, some of them, and they lower the activation energy. So that means that more of them have, when they do collide, have energy to react. So enzymes increase the efficiency of the collisions. Good job. How do we measure the rate of the reaction? I'm going to let you guys think about that. We talked about it at the beginning, and some of you guys weren't here yet. So I am recording, so I'll post this so you guys can watch that part. How do we measure the rate? And how does, that is a really good question too. How does refrigeration slow the process of food spoiling? Does anybody want to put that in the chat? Refrigeration is not a very old technology that we've had. We've only had it for the last, I don't know how many years, like 100. Before that, they had to have other processes like pickling, and they used salt to preserve the food. How does refrigeration slow down the process of food spoiling? It does slow the frequency down. Sienna's right. How does refrigeration slow down the frequency? What does it lower? I'm waiting to see if you guys have an answer for me. That's exactly right. Ariana got it again. It's cold, so it slows down the bacteria rate and just the decomposition without bacteria. So bacteria are going to reproduce less at a colder temperature. So if you freeze it, even better. You're not killing the bacteria when you freeze it, but you slow them down so that they can't reproduce. And also, like an orange rotting would slow down in the refrigerator because the collisions, the frequency of the collisions goes down. Very good. Okay, any questions on the first part? I'm going to do the second part also. Any questions on these? That's the end of those notes.